Imagine an engine that does not rely on combustion, magnets, or even electricity in the traditional sense, but instead is powered by light itself. Not just solar power converted to heat or electricity, but light directly driving mechanical motion through precision-engineered optical structures. This is the futuristic vision behind the idea of a light-powered, optomechanical engine composed of a myriad of high-Q microresonators, specifically devices that exploit whispering gallery mode WGM effects. But what exactly are WGM microresonators? To understand this, think of how a whisper travels around the curved walls of a cathedral dome without dissipating. In optics, WGM describes the way light circulates inside tiny spherical or toroidal resonators, confined by total internal reflection. When a photon enters such a resonator at the right frequency, it can bounce around thousands or even millions of times, creating a circulating electromagnetic field. The Q factor measures how many times light cycles through before losing energy. High-Q microresonators can trap light for long durations, producing strong optical fields with minimal input power. Now ask yourself, how can light trapped inside a microsphere do mechanical work? Here's the answer. Light carries momentum. When confined in a resonator, this circulating momentum can exert forces, known as optical gradient forces or radiation pressure, on the walls of the structure. In an engineered array of these resonators, photonic pressure can induce vibration, rotation, or even linear motion. In other words, photons can push. Now scale this idea. Suppose we create an array, perhaps thousands or millions, of WGM resonators all tuned to resonate with specific light frequencies and arranged so that their tiny oscillations combine in a synchronized fashion. Could this system act like a macroscopic optomechanical engine, converting coherent laser light into useful mechanical output? The concept may sound exotic, but recent advances in nano-optomechanics have brought it closer to feasibility. Research has shown that single WGM microresonators can achieve measurable mechanical oscillations, cooling, or actuation when pumped with lasers. Some even achieve quantum-limited motion detection. The combination of many such units, possibly on a photonic chip, could, at least in theory, scale these effects to create an engine powered entirely by light. But here's a challenge: efficiency and coordination. Each microresonator must maintain an ultra-high Q factor and resonance stability, or energy will be lost. Synchronizing many resonators to work in concert without interference or destructive coupling is another hurdle. Moreover, directing the resulting mechanical motion in a usable, macroscopic way is a non-trivial problem in materials science and engineering. You might now wonder, could such a light engine lift something or power a small machine? If current optomechanical torque experiments are scaled correctly, the output forces are still tiny, on the order of piconewtons. However, in space, microgravity environments or nanoscale devices where friction is minimal, even these small forces could be revolutionary. Picture future spacecraft components or smart dust robots powered and steered solely by directed light. This brings us to the speculative edge. If such systems can be fabricated with high precision, using, for example, photonic crystals, microtoroids, or silica microspheres, they could potentially operate as reconfigurable microengines, tunable by wavelength. Moreover, coupling these devices with nonlinear optical materials or quantum dots may allow for energy storage, frequency conversion, or even quantum control. So let us ask one final question: is this concept science fiction or a glimpse of what is coming? Answer: it is not science fiction. It is visionary applied photonics. While the full-scale engine is not yet realized, all the components, high-Q microresonators, WGM physics, optomechanical coupling, and array fabrication exist in laboratories today. What is missing is the integration and energy management strategy to bring them together. With continuing progress in photonic chip engineering, microfabrication, and materials science, A light-driven optomechanical engine is a matter of design, not impossibility. WGM resonators confine light through continuous total internal reflection, allowing photons to circulate around the periphery of a dielectric structure, such as a microsphere or microtoroid. This geometry enables extremely high-quality Q factors, meaning light can orbit many times with minimal loss, resulting in strong optical fields. The confinement boosts interactions between light and matter, enabling applications in sensing, lasing, and optomechanics. These resonators support multiple transverse modes whose coupling can be engineered for desired energy transfer dynamics. Light, stored in WGM modes, exerts radiation pressure on the cavity walls, forming the basis for optomechanical effects. A silica microtoroid with a Q factor of 1/8 can confine light for several microseconds, generating significant optical forces. Like sound waves trapped in a whispering gallery dome, light can circulate in microresonators and build up strength without escaping. Radiation pressure from circulating photons induces mechanical deformation or vibration in the cavity wall, a phenomenon known as cavity optomechanics. High Q resonators enhance these interactions due to the prolonged photon lifetime and coherent buildup of force. The mechanical motion, in turn, modulates the optical properties, creating feedback that can lead to cooling, amplification, or oscillation. This interplay is governed by the optomechanical coupling constant and the cavity detuning. Such bidirectional coupling allows for the conversion of light energy into mechanical work at micro or nanoscale. In a typical setup, a 980 M laser can drive mechanical oscillations of a microdisc resonator at minutes frequencies. Like wind pushing a swing, the light pressure continuously nudges the cavity walls, setting them into motion. To function as an engine, the system must cyclically convert optical energy into mechanical motion and extract usable work. This requires synchronization of optical driving with mechanical modes to create a thermodynamic-like cycle, such as oscillation, rotation, or translation. The resonators can act as pistons, where radiation pressure is modulated over time to generate net displacement. Collective synchronization across many resonators enables macroscopic effects such as thrust, fluid pumping, or rotation. Efficiency is governed by optical power input, coupling losses, mechanical Q factors, and thermal noise. Arrays of optically driven resonators have been shown to generate microflows in fluidic channels by vibrating in phase. Like steam engines use expanding vapor to push pistons, here light waves create optical pressure that actuates mechanical elements. Integrating thousands of high-Q microresonators into a coherent system introduces challenges of synchronization, coupling, and fabrication uniformity. To maintain collective dynamics, resonators must be phase-locked or coupled via shared optical or mechanical pathways. Variations in resonance frequencies due to fabrication tolerances can be tuned with thermal, electrical, or optical techniques. At scale, these resonators can exhibit collective modes akin to phononic or photonic crystals, enhancing or localizing energy. Achieving coordinated action enables macro-scale functionality such as propulsion or on-chip energy harvesting. Photonic crystal slabs with arrays of microdisks have demonstrated coherent light scattering patterns from synchronized WGM modes. Like a choir must sing in tune to produce harmony, microresonators must oscillate coherently to yield useful work. Nonlinear optical phenomena like Kerr effect, optothermal modulation, or optical bistability become prominent at high circulating powers. These effects can be harnessed to switch between operational modes, enhance coupling, or stabilize resonator performance. In some designs, nonlinearities are necessary for frequency conversion or feedback regulation. Resonance tuning also enables frequency selectivity, mode matching, and rejection of noise, which are crucial for maintaining engine efficiency. The interplay of optical and mechanical nonlinearities can lead to complex behavior such as chaos or mode hopping. Optomechanical instabilities can lead to self-sustained oscillations in microdisks above a certain input threshold, like a guitar string going into harmonics when plucked hard. High energy in resonators can trigger unexpected but usable dynamics. Materials with low optical absorption, e.g., silica, silicon nitride, and high mechanical quality are preferred for low-loss operation. Fabrication requires sub-nanometer surface roughness to maintain high Q factors, often using lithography, etching, and reflow processes. Integration with photonic waveguides allows efficient coupling of laser input and signal readout. Thermal and mechanical stability must be ensured to avoid mode drift or loss of coherence. Scalable fabrication remains a challenge for large arrays, while maintaining resonator uniformity and functionality. Fused silica microspheres can achieve Q factors greater than 109, but require precise CO2 laser reflow to form perfect spheres. Like building a watch, microscopic precision is needed. Every gear must be shaped and placed flawlessly. Optical absorption generates heat that can shift resonant frequencies, degrade Q factors, or damage the device. Passive cooling through substrates, active cooling using Peltier elements, or dynamic feedback loops are required to maintain performance. Thermo-optic effects can be exploited for fine-tuning but must be managed to prevent thermal runaway. Mechanical modes are also thermally sensitive and can be destabilized by ambient vibrations or thermal fluctuation. Stability is vital for sustained and repeatable energy conversion. Microtoroids heated by pump lasers exhibit red shifting of WGM modes due to thermal expansion and refractive index changes. Like a race car overheating in a tight loop, the system must dissipate heat or risk falling out of tune. The Carnot efficiency analogy can be applied to optomechanical engines operating between a hot photon bath and a cold mechanical mode. However, real systems face limitations from photon leakage, thermal noise, imperfect coupling, and decoherence. Quantum backaction sets limits on simultaneous measurement and control, particularly in quantum optomechanical regime. Efficiency can be improved by using resonators with stronger optomechanical coupling, G0, minimizing losses and exploiting cooperative effects. Modeling involves solving coupled differential equations for optical fields and mechanical motion under driving. A theoretical engine composed of silica microdisks was predicted to reach 20% conversion efficiency under ideal conditions, like trying to extract work from ripples in a pond. You can, but only if the waves are strong, coherent, and well-contained. Applications include chip-scale actuators, microfluidic pumps, vibration sensors, optical gyroscopes, or photonic propulsion devices. A light-driven array could theoretically act as a microthruster or molecular transport engine in lab-on-chip devices. For large-scale use, integration with waveguide networks and energy harvesting optics is essential. The field is still experimental, but small-scale proof-of-concept systems have demonstrated viability. As material science, nanofabrication, and AI-based feedback improve, the feasibility of optomechanical engines powered by light becomes increasingly tangible. A prototype optomechanical engine based on gas, microresonators, has been used to drive submicron oscillators with piconewton forces. Like sails catching wind on a nanoscale ship, light can push tiny components to work together in orchestrated motion.